So, good day everyone. My name is Samal TK and my teammates are Ajay Kumar and Shashank K. Gowda. And our concept of bringing the optimization technique is Tabu search algorithm. So, what is Tabu search algorithm means? It's a meta heuristic method in the sense it uses some heuristic in the sense it's a value that is used to explore the next coming steps. It's a commonly used meta heuristic used for optimizing model parameters. It's a popular method for optimizing model parameters. A meta heuristic is a general strategy that is used to guide and control actual heuristics. There's a difference between non-heuristic problems and heuristic problems, where non-heuristic in the sense we have to explore every possible solution in case of artificial intelligence and computer science or optimization techniques. Heuristic is a value that is used to explore only limited amount of search techniques, which is its algorithm. In computer science and mathematical optimization technique, a meta heuristic is a higher level procedure or heuristic design to find, generate, to provide a sufficiently good solution to an optimization problem. In AI ML problem, it doesn't rely on any of the type of problem. This can be a particular example for Tabu search or ant colony optimization problem. Tabu search is a heuristic search method employing local search used for mathematical optimization. Let's come to the background of optimization techniques. This was invented or proposed by Fred Glover in 1986, but this algorithm was formulated in 1989, which comes near to 1990s. Uh, 1990s, this Tabu search algorithm became popular and it was widely used because it was one of the optimized way of searching algorithm. Nowadays, it is one of the most widespread meta heuristics. The use of memory represents a particular feature of Tabu search. Uh, Now let's go why we need the Tabu search algorithm. It's an optimization technique that uses a guided local search procedure that avoids local optima and rejects moves to points already visited in search space by the means of Tabu list. What is the Tabu list here? We can explain is that which is all the nodes, or you can say we can say the nodes in the short term set that is already visited, particularly in while solving the problem. Tabu search list is a short-term set of solutions that have been visited in recent past. The number of previous solutions can be stored. It's just like a stack or queue data structures. It explores the solution space beyond local optimality. More flexible. This Tabu search list is more flexible compared to all other non-heuristic methods. This search behavior is used in adaptive memory so that Tabu search algorithm won't stuck in suboptimal region. There's hill climbing algorithm which will be going in the next part. Yeah, there's two types of search techniques, which is convex and non-convex method. Here in this slide, we can see that there's only one global optimum over here because there's no particular like two or three peaks in a hill. This non-heuristic algorithm like hill climbing works fine in convex space. It is able to find the global optimum. If we come with the part of non-convex problem, there will be a local in this type, it fails to reach the global optimum because it works only in convex space and assumes that local optimum as a solution. Here we can see there's a local optimum and a global optimum. What other non-heuristic algorithm does is it only goes to the first pick and stops there, thinking that that is the global optimum, which gives the wrong result basically. That's why we use a Tabu search algorithm so that it goes to the next peak as well and finds the global optimum at last. That's why we need heuristic or meta heuristic or algorithm like Tabu search. Next. In case of non-heuristic algorithm like hill climbing, we can't move forward from the current position because if we move forward, the function value will become low. So it stays in local optimum and can't find the global optimum, as I said in the previous slide itself. In heuristic method like Tabu search, it saves the current position or solution in Tabu and prohibit that again and again and take step in step to find global optimum. Here the correct integral what is there, it is next goes to the it travels the Tabu search algorithm basically moves to another peak in the hill climbing and finds the global optimum. This is the main basic concept of Tabu search algorithm. The next part will be continued by Ajay.
Morning everyone. I am discussing the basic utilities of Tabu search. There are four ingredients: Tabu list, aspiration criteria, Tabu tenor, and candidate solution or the neighborhood solution. First of all, what is Tabu list? Tabu list which keeps the track of the recently visited solution or points, which avoids the revisiting of the solution in the Tabu. Prohibits the some case. It prohibits some cases in criteria. Tabu tenor. When the visited solution is pointed, it's added to the Tabu list and it is associated with some value, so that for some iteration it will be not considered. With each iteration, the Tabu tenor decremented by one. When it becomes zero, the solution or the point remains from the Tabu list, and we can reuse the or revisit that point. We can set the Tabu tenor in two ways. One is static, another one dynamic. Static means choose t to be constant, that is square root of t. Dynamics choose t randomly between t max and t min. Next, aspiration criteria. Sometimes we need to allow the taboo moves. Means if any move or solution in the taboo that won't be allowed, but sometimes we have to allow that moves because, for example, the given moves if providing global solution are allowed to are all the moves which are worse than the given taboo move. On that situation, we allow the taboo moves means forbidden moves. Next, candidate solution or neighborhood solution. Candidate solution or neighborhood solution is the solution which is obtained by the swapping of variables or moving the solutions from the current solution to the feasible solution. Tabu search stopping conditions. When the no feasible solution in the neighborhood solution of I is found, we need to stop this tabu search. When k is larger than the maximum number of the iteration allowed, then we want to stop the tabu search. The number of iterations in the last improvement of the current solution is larger than the feasible number, then we need to stop the tabu search. And if any evidence found that the optimum solution has been found, then we need to stop this tabu search. This is the algorithm of our Tabu search algorithm. First, we initialize the current solution to the X. The current solution may be any feasible solution that applicable for a criteria that meets some criteria for acceptable solution. The next step is generating of set of neighborhood solution, means candidate list of neighborhood solution to the current solution. This can be done using the removing variables, interchanging variables, swapping of variables, and many based on the problem statement. The next step is to find the best solution S dash from the candidate list. When we create the neighborhood solutions, we need to choose the one best solution from among the candidate list of solution. Then next step is to check whether this S dash is present in the Tabu list or not. Basically, Tabu list contains the moves or the solution which are already visited. So that if it is S dash is already present, it means it already occurred in previous steps. So we won't select that, and we go to step 4 and choose another best solution. If not, then we replace the S with the S dash. That is new solution. Then update the Tabu list with the new solution or a new move or new point, whatever based on the problem. Next, check whether the stopping criteria is reached or not. Stopping criteria means whether the iteration is max iteration reached or indication of the global maximum is reached. These are the stopping criteria. If that means reached, we need to stop. If yes, then we stop the process and output the solution. If no, we go to the step 3. Last step is outputting the solution. This is the flowchart of the Tabu search algorithm. As I said, first we initialize the solution to I, then create the list of candidate solution using the current solution. Then we evaluate that solution and choose the one best admissible solution from that candidate solutions. If that staffing condition is satisfied, we proceed to final solution. We out that solution. Otherwise, we update the table with the current solution and update the aspiration conditions. Let's uh, let's see. Just understand the algorithm with the example. Here the problem is minimum spanning tree problem with constraint. Objective is to connect all the nodes with the minimum cost. There are two constraints in here. Constraint one is link AD can be included only if link D is included. That means if we want to add the link or edge AD without having the edge DA, then there will be penalty of 100%. Then the next constraint is at most one of these three links AD, CD, and AB can be included. If all three edges are included, then there will be 200 of penalty. If only two among these are included, then there will be 100 of penalty. This is our problem statement. This is our initial graph. This is an optimal solution without considering the constraints. Now, now let me solve this. This is the initial graph, initial spanning tree without considering the constraints. Now we want to create the candidate solutions using this current solution by adding the edge and deleting some edges. First, before moving to that, we have to know the cost of this minimum spanning tree. We can see that A to B is 20, A to C is 10, that is 30, A to D is 50, 45, and C to D is 50, that is 50. The cost is 50 and the penalty is 200 because they have the edge BD without having the edge DE, and there is second if you violate the second contract also, we having among three restricted edge we have the edges AD and AB, so there is the 100 penalty, total of 200 penalty plus 50. So the iteration on cost is 250 total. We need to create the candidate solutions or neighborhood solution by adding or deleting the edges. First, there are three edges that could be added and deleted. If we add DE, it creates a cycle. It violates the constraint of the minimum spanning tree. So that we need to delete the one of the edges AB, AC, or CE. First, we try to remove the edge CE. Now, if we remove the edge, there is no cycle. Now we want to find the what cost for that this tree. Now A to B is 20, A to C is 1030, and A to D is 50, 40, 45, and B to E is 30, 70, 75. Total cost is 75 plus 200 penalty because we have the AD to having the DE, and among the three we have two edges AB and AD, so 100 penalty. Total 200 penalty plus cost is 75. Now we will try the same to the edge AC. By removing this edge, we have the cost of A to B, we have the cost of 70 and the penalty of 200 because as the constraint states we having AD without D and two edges, so there's 100, 470. We do same for the B, adding B and deleting AB. Adding D and deleting AB. Deleting AB, this also cost A to C is 10 and B to E is 30, 40 and C to E is 45 and A to D is 50. 45 plus 50 that's 60. plus 100 of only here your penalty is only 100 because it has only one edge AD without having DE, and second function is not violated. We having only one restricted edge. Among these three edges, we have only one edge, that is AD. If we have AD and AB and CD three in whether, then it will be a 200 of penalty. In this solution there is no such case, so there is a 100 penalty. Total cost is 160. This is one step. Now you have to do for the same CD adding of, if we add the CD, leave CD. You can see that there is a formation of cycle here. We need to remove one of the edge AC or AD. When we add, we try to remove the edge AD. Now calculate the cost. By removing AD we got the 160. By removing AC, by removing AC, we can calculate now that they're becoming 65 normal cost and 300 penalty because we are having AD without having DE and three restricted edges also added in at the same time. So there is 100 plus 200 penalty, 300 plus normal edge cost is 65 to 365. For the current solution, for the original solution, we also do for the same for the DE also. Adding of DE, adding of DE, when we add the DE, there are the comes cycle. So we need to remove one of the edge AC, CE or CD. When we remove the AC, CE or AD, when we add the D and deleting the C gives the edge cost of 85 and penalty of 100, so that's 185. Adding of D and deleting AC gives the edge cost 80 and penalty of 100, so 180. Adding of D and deleting AD gives the edge cost of 75 with no penalty because when we add D and remove AD, there is no constraint violated because we don't have AD without having the especially we don't have the AD, so there is no first constraint is violated. And among three restricted digits, that is AB, AD, and CD, we have only one edge, so there is no penalty. So penalty is 0 and 75. Among these all candidate solutions, we need to choose one best one. The problem is to minimizing, so that we choose the 75 as the our solution. That is adding of DE and deleting AD. Adding DE and deleting AD can be done. Now we will go to the next iteration by adding this DE into Tabu. Here Tabu can be selected as 3, that is to randomly choosable. It means for 3 iteration DE should not be considered except some conditions like all the other moves are worst except this DE move. In the next coming iterations, then only we consider DE or any other moves which are present in DE. If that's not a case, then we don't choose the move in the Tabu list. Now this is the solution by 75 as I calculated previous. This is our previous. It is obtained by adding D and deleting AD. Now we want to create the candidate solution for the same. By there are 3 edges. There are D, CD, and AD. Adding of AD, adding of B, adding of AD, adding of CD. First, we try to go with adding AD. When we add AD, there are this forms cycle, so that we need to we need to delete the one of three edges. So we start with deleting DE. DE is already presented in the Tabu. Also, we create we solve this. If among these solved solutions, if Tabu move becomes very less, then we need to consider that move based on the aspiration criteria. Here, that's a larger value 250 compared to these two. That's why we mentioned this as a Tabu move. Adding AD and deleting DE gives the cost of 50 and penalty of 200. It also in the Tabu, so that it's considered as a Tabu move. Next, adding of AD and deleting CE. Now the edge cost is adding of AD and deleting CE is 85 and plus 100 penalty because we have the edge we have the both two edges AB and the AD both along with constant one is not violated because we have the AD with the DA, so the constant one is not violated. Here constant two only violated with the only two edges, so the penalty is 100. Penalty is 100 here. Now next choose the next solution. The next is add AD and delete AC. Now they calculate the edge cost. This edge cost becomes 80 and penalty of 100. That is 180. Now we do same for the BE and CD. If we add BE once cycle, so that we need to remove the one of three edges. We delete one edge and calculate the its cost. First we deleting CE gives the 100 as the cost. Deleting AC gives the 95 as the cost, and deleting AB gives the 85 as the cost. And remaining CD for CD to be it also forms the cycle. So we need to remove these two edges, one of the two edges. By adding this, we need to remove one of the edges. First, we try to removing D. As I mentioned, D is also in Tabu, but giving the best solution compared to this. Based on aspiration criteria, we consider the separate Tabu or forbidden moves when it is best among all others. Here, D is also considered not considered as Tabu. After doing this, we need to again check for the best solution among these all the candidate solution. Here 85 is the best solution, that is adding BE and deleting AB. Adding BE and deleting AB means adding BE, deleting AB gives the best solution for the iteration. So we add the DE to the Tabu list. Where DE becomes 2 because for each iteration, as I mentioned earlier, Tabu tenor will be incremented by 1. 3 will become 1 and B is added now, so that is 3. For the iteration 3, which is obtained by the iteration tool, the cost is 85 as I mentioned here. Now we need to do the same removing and adding the edges to create a candidate solution. Here there are three edges left out. First one is AB and AD and the CD. First, we need to add AB. Adding AB causes the minimum cycle in the tree. So we need to remove one of these edges. Add KB and delete B. Leave B is in the tabu list, so that is considered as the tabu means it is already a executed solution. Then add AB deleting C gives the cost of 100 and the penalty is 0 because adding AB and deleting C. There are no constraint violated, and that's why the penalty is 0 and the cost is 95 all for all. Now we do same for the other remaining edges, which are AB. Let me explain here. Okay. Adding AD and deleting AD gives the solution of 160, which is the worst among the. It is also in the D, so this we consider it as a tabu move. And AB, adding AB, deleting CE gives the 95 as the adding AD and deleting AC gives the 90 as the result. Adding CD and deleting CE is 70 gives the resulting as the 70, and adding CD and deleting gives the cost as the 105. As D is already present in the tabu list because it's giving the best solution compared to all other. That's why we do not considering this as the tabu or forbidden move. So we are considering D. Now D becomes one, and C we add the CD to the tabu and it's left for the 3 iteration. This is the final solution because once we consider the tabu as D, it reaches 3 iteration. So optimal solution is adding CD and deleting DE in the from third iteration, from the resultant of the second iteration, which gives the cost is 70, which is minimum of the all the previous iteration. As we see here, this gives 70, 85, it gives 75, and the previous cost is one initial cost is 165 or something. So the optimal solution cost is 70. Additional iteration is only finds the inferior solution. That's why we stop here. That's all about the solution solving this problem using the Tabu search algorithm. The next part will be continued by the Shashank.
I'm myself Shashank. So some of the examples to solve with Tabu algorithm. NQ problem, traveling salesman problem, minimum spanning tree, assignment problem, vehicle routing, and DNA sequencing. These all examples of Tabu's algorithm. And next, advantages and disadvantages. So some of the advantages are it can escape local optimum by picking non-improving solutions, and it can be used to avoid cycles and reverting to old solutions. It can be applied to both discrete and continuous solution. These are the some advantages we can see in Tabu's algorithm, and some disadvantages are the number of iteration can be very high and lot of turnable parameters in this algorithm we can be seen. So these are some disadvantages we are going to see. Thank you.